Good morning, all. I'm recording this on a Sunday morning. That's why I'm saying good morning. So, this is a video for my younger viewers, those who are taking the international GCSE test. And I think the only one left is paper 2, which is from what I saw online, and let me know if I'm wrong. You guys are taking this on June the 15th, okay? So, it's paper 2. It says paper 2P. I think the letter P has to do with the region, but let me know what you think. And what else do I want to say? Okay, the test lasts an hour and 15 minutes, so that's 75 minutes. So to stay on time and to achieve maximum score, try to spend as many minutes in a problem as the problem awards marks. What I mean is that if a problem awards 10 marks, try to spend 10 minutes on it, okay? So you stay on time. Another thing I say, especially for you guys who are younger, don't panic. Go through the problems, read them. Make sure you read them and understand them really well, okay? So half the answer is in the question, as I say, okay? So read the problem carefully, make sure you understand what they're asking, and try to solve it. If you cannot solve it, skip it, okay? Don't waste time, because not only you waste time on something that you cannot solve immediately, but you also lose momentum, and your psychology starts to go down, and so on. So it's better to work on the problems you know how to solve first, and then return to the ones that you don't know how to solve in the end. And also make sure you read all these formulas they give you. So there is a formula page in the front of the paper, and then there are some more formulas at the back. Okay, so it's good to have in mind, to have some classification in your head. Okay, this problem deals with forces and motion. Okay, so then this means that you will have to find the formula needed here. Or if a problem is related to electricity, then you should be able to find the formula you need in the electricity section, and so on and so forth. So make sure you actually read it, read these formulas, because sometimes you might get inspiration to solve the problem. So what else is there to say? Another thing is for problems that involve just writing sentences, justifying a statement, or defining something, etc. So if the problem awards 1 mark, 1 sentence is enough. If it awards 6 marks, you need about 6 sentences. So anyway, so let's start. I have been talking for too long without doing anything. So first question, it's a multiple choice question. So this question is about nuclear decay. And the question goes, which of these is the same as a beta particle? Okay, the beta particle is an electron. Okay, so this is something you should know. I don't know if there is anything else to add here. It's definitely not an electromagnetic wave, not a helium nucleus, and not a neutron. Okay, that's another thing with multiple choice questions. There are not too many in the GCSE tests from what I saw. But those of you who are going to go on to take the AS and A-level tests, there is a devoted section in the beginning of each test that is only multiple choice. So one of the tricks is to eliminate all the wrong answers to arrive to the correct answer. Okay, B. Which of these is the same as an alpha particle? It's not an electromagnetic wave, but it is a helium nucleus. Okay. By the way, a trick that they might, a trick question might be something like, maybe one of the options will be helium atom, okay? That's not an alpha particle, because the helium atom involves the electrons orbiting the nucleus, so the helium atom is actually not the alpha particle. The alpha particle is just the helium 4 nucleus, so 2 protons and 2 neutrons, okay? C. Complete the nuclear equation for an alpha decay. Okay, on the left-hand side, we have americium 241. Okay, and on the right hand side we have neptunium 237, therefore we need another 4. We anyway know that the alpha particle has 4 nucleons, 2 protons and 2 neutrons. Okay, so as I just said, we know that the alpha particle has 2 protons, and to balance the equation we need neptunium to have 93 protons, because 93 plus 2 is equal to 95, which is the proton number for americium. Okay, first question is done. Let's move on. Question 2. The diagram shows a rod and a cloth. When the rod is rubbed with the cloth becomes positively charged and the rod becomes negatively charged. Explain how the cloth has become positively charged. So, 2 marks, okay? So this is an example of a question that involves writing down sentences to describe a phenomenon. So we need 2 sentences, but I'm going to provide 3, okay? So when you rub the rod with the cloth, okay, electrons transfer from the cloth to the rod, okay? Let me switch that off, okay. From the cloth to the rod, okay? I will need an extra page to continue with the other statements. So the cloth loses electrons, okay? So it now has more protons than electrons. Okay, and the last statement we can write is that an object with more protons than electrons carries a net positive charge. Okay, so that's a complete answer to question A. Let's move to question B. The negatively charged rod makes contact with a metal object connected to the ground. There is an ammeter in series with the object and the ground. Explain why the ammeter shows a current for a short time and then shows no current. So let's write that the rod is negatively charged. We already know that. So the rod, let me try to make better letters. So the rod carries a negative charge. Oops. Okay, which means it has excess electrons. Okay. When it contacts the metal, okay, when it contacts the metal object, sorry, connected to the ground, okay, those excess electrons, oops, those excess electrons flow through the metal, flow through the metal towards the ground. Okay, and another sentence we can write, I will move to the back. So this is question B and I continue there. Once the rod has once the rod has discharged completely, okay, there are no more electrons to move, okay, so the current drops to 0. Okay, so we are done with questions A and B. Let's move on. Part 2 of part B. State the formula linking charge transferred, current and time. So Q is I times time. And this is the example. This is an example of a question that verifies what I told you in the beginning. So when I said that you should check these formulas, so I'm pretty sure we can find this formula somewhere here. Is it here? No, it's not here. So I was wrong. Let's go to the back of the paper and check again. So electricity, there it is, okay? So just by reading the formulas they give you, you can find answers that give you points, guys, okay? You don't say points, you say marks for the British papers, I guess. In case you haven't followed my previous videos, I lived in America for a huge chunk of my life, so I'm more accustomed to American standards. So anyway, part 3, the mean current displayed on the ammeter is 6.8 times 10 to the negative 6 amps. The current lasts for 3.7 milliseconds. Calculate the charge transferred. Okay, so here we just apply the formula we just wrote down. So Q is equal to the current, 6.8 times 10 to the negative 6. And when I solve problems, I put all the numbers to the left and all the units to the right. So the amps go here, okay? Times 3.7 times 10 to the negative 3 seconds, okay? And this is equal to 2.52 times 10 to the negative 8. 1 amp is 1 coulomb per second, so the seconds cancel, and the final answer is 2.52 times 10 to the negative 8 coulombs. Okay, this was problem 2. Okay, question 3, part A, asks us to state the principle of conservation of momentum. So we can write that in a closed system, in a closed system, the total momentum before a collision equals the total momentum after a collision. Okay, nice and simple. When we say closed system, in case it confuses you, it means like, let's say we have one car heading towards another car and they bump together. Okay, that's a closed system. If during the collision there was a meteor falling onto one of the two cars during the collision, for example, that will not be a closed system, okay? Because it involves something, an outside factor coming into the system, okay? So closed means nothing else interferes with the process, okay? B, the diagram shows object A and object B moving in opposite directions. The arrows show the direction of the velocities of the two objects, okay? Before the collision, object A has a momentum of 39 kilograms times meters per second. After the collision, object A and object B stick together and stop moving. State the magnitude of the momentum of object B before the collision. So it will be actually 39 kilograms times meters per second. And the reason is that, let me see. So this guy moves to the right with 39 kilograms times meters per second. So if after the collision they stop moving and they stick together, this guy has to be moving with 39 kilograms times meters per second, actually minus, but the minus refers to moving in the opposite direction, okay? So the magnitude of the momentum will be 39, okay? So that's the answer. Part 2, state the formula linking momentum, mass, and velocity. So this is a free mark that you can get. So momentum is mass times velocity, okay? And it's also in your formulas in the back of the paper, okay? Part 3, the mass of object A is 8.1 kilograms. State the velocity of object A before the collision. So we need to solve for V. So V is P, momentum over mass. So 39 over 8.1, and we have kilograms meters per second, and then kilograms in the denominator. So that cancels, and we get 4.8 meters per second. Part 4, the time taken for the collision is 0.56 seconds. Calculate the average force on object A. So object A goes from 39 kilograms meters per second to 0 in 0.56 seconds, okay? So the force is delta P over delta T, okay, which is equal to 39 over 0.56. And that's kilograms meters per second, and then we have to multiply with seconds in the denominator, and that's equal to 70 kilograms meters per second squared, which is 70 newtons, okay, because the newton is equal to kilograms meters per second squared. Okay. 5. Give the direction and magnitude of the force on object B from object A. Okay. Let's, do I have enough space? So by Newton's third law, if object B exerts a force, okay, a force on A, comma, then A exerts, you don't have to write this down during the test, by the way, I'm just explaining things. So B exerts a force on A, then A exerts an equal but opposite force on B. Okay, so the magnitude is 70 newtons and the direction is to the right. Okay, so that's the answer. Question 4. Diagram 1 shows a Hertzsprung-Russell diagram. Okay, and we see the absolute magnitude of the stars to the left and the temperature the absolute magnitude is on the y-axis and the temperature on the x-axis. I don't know what's wrong with me today. Okay, and the absolute magnitude actually increases in the opposite direction. Okay, we go from -5 to 15, but -5 are the brightest stars. Okay, so that's a little bit confusing for students sometimes. And also temperature increases to the left. Okay, so for example, if I take these stars in the red circles down there, those are actually the coldest and the less bright. Okay, so yeah, that's the general idea. So let's go read the questions now. Okay, A, draw a cross to show the position of the sun on the HR diagram. So the sun has a magnitude of about absolute magnitude. It has an absolute magnitude of about +5. So it's somewhere here. So if you draw a line, so that's the position of the sun. Okay, 2. In approximately 4 billion years, the sun will enter the next stage of its evolution. I never taught at the GCSE level. I only taught AS level, A level, and university. So I don't know if they teach you these things at this level, but the reason this will happen is because the sun will burn all of its hydrogen in the core, and it will expand because of that. Okay. So draw a circle on the HR diagram around the area that will include the sun in the next stage of its evolution. So it's over here actually. Okay, so sun at the next stage. Okay, and the next stage is called the red giant stage. Okay, part B, describe the stars that are in the top left corner of the HR diagram. So when I started describing this problem, I mentioned that those are the most bright stars actually. So let's write, and the hottest. So very high, so those stars have a very high surface temperature, so they're hot. They have a very high luminosity. Very high luminosity. Okay. And also very high absolute magnitude. Okay, they are blue or blue-white. The reason for that is that blue, I mean, if you think about it, the UV light is the most dangerous, right? Why? Because it's the hottest, okay? Has the most energy. So since these stars are really hot, they are blue, and they have a very high mass. I don't know if they teach you this. I'm not going to write it down, but these stars also burn really fast. We're talking about millions of years, whereas the sun and stars that are like the sun burn for 5 billion years. So that's 1,000 times more. Okay. So, I mean, as they say, both in life and for stars, the star that burns the brightest burns the shortest, something like that. There's an expression. Let me know in the comments. By the way, speaking about comments, guys, please like and subscribe. Let your friends know about these videos. I mean, I'm trying to make this channel viable. It's not viable yet, but I'm trying. So, and let me know if I'm doing a good job also, because I'm feeling a little bit uncomfortable with the GCSE level because I've never taught it and etc. But I mean, it's not hard. It's just that I don't know how much I should tell you about the physics of these problems. So let's move on to the next part. Okay, see, diagram 2 shows how the brightness of two stars, A and B, changes with time. These stars are called Cepheid variables. Okay, and we see that they kind of oscillate right there. Okay. Part 1, determine the period of the variation in brightness of these stars. Okay, so the period is from one maximum to another maximum, or one minimum to another minimum. I have the tendency to use the minimum. So you see that that's one period. It looks like it's 150,000 years, but let's take an average. So, okay, so the first measurement we find is 150,000. And then if we check the next oscillation, it goes from there to there. That's a little bit more than 150,000. So that's about 160,000, I would say. Okay. Is that correct? Let me see. So every little square right there is 10,000 seconds, right? Because we have 310, 320, 340, wait, 310, 20, 30, 40, 50. Yes, so it's 10,000 seconds per small square like that. So that's 160. And then the next one is, again, it looks like 150. Okay. Now let's check the other star. From there to there, it's 150, but then it becomes 160. So let's take these two values only and call it a day. And 150,000 seconds sound good. Okay. I'm pretty sure if you write 150 or 160, they will take it as correct as well. So you don't have to do this average. I did it like that. Okay. 2. Calculate the frequency of the variation in brightness of these stars. So F is 1 over T. So that's 1 over 150,000. So that's 6.5 times 10 to the negative 6 hertz. Okay. Let's go to question number 3. State what is meant by the term absolute magnitude. So absolute magnitude, okay, is the brightness an object will have, okay, if it were observed, okay, from a standard distance from Earth. Okay. Now, part 4, star A and star B have the same absolute magnitude, but star A is always brighter than star B in the night sky. Explain how this is possible. So, okay, absolute magnitude is measured at a fixed distance. Okay. So both stars, in this case, okay, so both stars have the same intrinsic brightness. And I don't know if they teach you this. This standard distance is 10 parsecs, okay? So that's about 32.6 light years away. Okay, that's a huge distance, by the way. Okay, their apparent brightness, it's the second thing we want to write. So their apparent brightness in the night sky, okay, depends on how far they actually are from us. Okay, so star A appears brighter, okay, because it is closer to us than B. Okay, and that's the answer. So the absolute magnitude tells you how bright a star really is. So, for example, the apparent magnitude, the apparent brightness, tells you that the sun is the brightest star in the sky, right? But it is not. I mean, there are other stars that are more bright, but they are farther away. Okay, so the absolute magnitude is what actually tells you how bright the star really is. Okay. Can you make an analogy with human beings? I mean, when it comes to stars and celebrities, I can't think of anything clever right now, so I'm gonna let it up to you. So let's move on to question number 5. Question 5, diagram 1 shows the apparatus a student uses to determine the specific heat capacity of a liquid. Okay, so we have a power supply, voltmeter, an ammeter, a lead. We have a liquid there, the electrical heater, okay, the thermometer, and insulating material. Okay, that's a lot. Okay, part A, describe a suitable method the student could use to determine the specific heat capacity of the liquid. So let's start by stating that we need to use a balance, okay, to find the mass of the liquid. Okay. And the technique you should use is to weigh the container with and without the liquid and subtract. Okay, record the initial temperature. The initial T, okay, from the thermometer. Okay, switch on the heater and record the voltmeter and ammeter, okay, readings, along with the time using a stopwatch. Okay, because you have to switch this on and heat it, right? So you have to record the voltage, the current, and the time taken to heat. Okay. Record the final temperature. So record the final temperature once you decide to stop heating. Okay, once you record the final temperature, calculate delta T, which is T final. Let's call this T final and let's call this T initial. Okay, so delta T is T final minus T initial. It's the temperature change. Okay, I will need extra space. Okay, also calculate the energy supplied, and you can do that using energy is current times voltage times time. Okay, so you will record the current and the voltage from the meters and the time from the stopwatch. Okay, now energy is C, the specific heat capacity, times the mass times delta theta, right? So the specific heat capacity is equal to the energy that you just calculated over the mass that you recorded with the balance times delta theta. And that way you can find the specific heat capacity. A few more things though. Repeat the whole experiment. Okay, and average your results. Okay, for reliability. Okay, so you need to perform this a couple of times to make sure that your results make sense. And stir the liquid. This is something we should have written in the beginning probably. So stir the liquid throughout. Okay, so the temperature is uniform everywhere. Okay, so this is a complete, this is more than enough actually. I mean, we described everything, I believe. So if I forgot something, let me know in the comments, but I think this is a complete answer. Let's move on to part B. The graph shows the students' results. What is happening to the liquid between points P and Q on the graph? So as you can see here, the temperature is constant, it doesn't change. So that signals a phase change, okay, change of state. So this happens when we go from liquid to steam, to gas, okay, or from gas to liquid, or I don't know, liquid to solid, etc. So in this case, let me see. It cannot be melting because this is not a solid. So what's happening there is boiling, actually. Okay, melting, freezing, and condensing is not the case. So so this becomes gas. So the liquid becomes gas. Don't let the temperature fool you. It's 65 degrees there, Celsius. So this might be alcohol or methane. I don't know, some substance that becomes gas at 65 degrees Celsius. Okay. So it's not water, I'm trying to say, okay? And we know it's boiling because the temperature rises, okay? Meaning that it's a liquid that gets hotter and hotter until it reaches 65 and it boils, okay? I'm gonna erase that. Okay. All right. 2. Use the graph to determine the change in temperature of the liquid after 15 minutes of heating. Okay, so 15 minutes is that period, but we start from 30 degrees. Okay, so 65, as we just said earlier, minus 30. So the temperature change is 35 degrees Celsius. Okay. Part 3, the power of the heater is 48 watts and the mass of the liquid is 0.53 kilograms. Calculate the specific heat capacity of the liquid. So specific heat capacity, is 48 watts. Okay, and I'm gonna work out the units later. So 48 watts, and we were heating for 15 minutes. So 15 minutes, and every minute is 60 seconds. Okay, so that's that. And then we have 0.53, and that's kilograms. Okay, and the temperature change is 35 degrees Celsius. Okay. So if we work this out, we find 2,328.8, and then watts are joules per second. Okay, so the seconds in the numerator get cancelled, so we have joules per kilogram per degree Celsius. Okay, I actually haven't checked online what kind of liquid this is. Maybe you can check and let me know in the comments, okay? Figure out what kind of liquid this is. Just ask ChatGPT, probably will know. So a liquid has a specific heat capacity, and put that number in and it will probably tell you. Okay, or Google. Google will know too. Okay, so watts is joules per second. Okay, there. Because my handwriting is horrible sometimes. I'm sorry, guys. So let's move on to question number 6. Okay, question 6. The diagram shows forces used to turn a tab. State the formula linking moment, force, and perpendicular distance from a pivot. Okay, so a moment is defined as the force times the perpendicular distance perpendicular distance from pivot. Okay. 2. Calculate the total moment of the two forces required to turn the tub around the pivot. Give your answers in newtons times centimeters. So this force pushes to the left, so it wants to turn the tub to the left. And then this force pushes to the right, so it wants to turn in the same direction, okay? So this means that we have to multiply by 2. So we have 2 times 8.1 times 2.6 newtons times centimeters, which is equal to 42.1 newtons times centimeters. B, the tub is used to put some water in a bucket. Describe the arrangement and motion of the water particles in liquid water. You may draw a diagram to help your answer. So, water particles in liquid water, okay, are closely packed, okay, and touching, okay, but they are not in a regular repeating pattern, meaning that, the repeating pattern is observed in solids, okay? So their arrangement is random and disordered, okay? Particles move randomly and can slide past each other, okay? This ability to flow, okay, is what makes it a liquid water. This ability to flow is what makes it a liquid. Oops. Okay. So this was question 6. Let's move on to question number 7. The photograph shows a wind turbine used for supplying energy on a large scale. I have to say that I'm not fond of these turbines. Cyprus is full of them. They are ugly, not a clever solution to the energy problem. And I don't know, I just don't like them aesthetically. I don't know. I'm pro nuclear energy, guys. I know it's the devil, but I like it. Okay, it's clean and it's efficient. So, part A. Describe a change in the turbine's energy stores from when the turbine is at rest to when it's moving at full speed. So, the turbine is gaining speed. Okay, so its kinetic energy store increases. Okay, so the kinetic energy store increases. Okay, 2. Describe a change in the turbine's energy stores when the wind is blowing but the turbine moves at constant speed. So at constant speed, the kinetic energy does not change. Okay, so the wind is still doing work on the turbine. So energy is transferred. So energy is transferred to the thermal energy store of the turbine. So this is from friction and resistance. Okay. So in this case, the thermal energy store increases. Okay, let's move on. B, state the formula linking efficiency to useful energy output and total energy output. To useful energy, it should be total energy input, right? Something's wrong there. So anyway, so efficiency is useful energy output over Let me check the formula. I'm not wrong, right? It's a typo. Let me see. Not there, not there, not here, not here. So, oh, I'm wrong. Okay, so the efficiency is useful energy output over total energy output. The way I know it is with input, but anyway, okay, let's go with that. So I'm sorry, guys. Let's erase that and multiply by 100 and then divide by total energy output. Oh, I know why I got confused. Okay, so total energy output is how much energy a machine provides. Okay, so in my case, I think about it as input to the system. Okay, so it's the same thing, but it's a subtle difference. I'm sorry. So part two, the wind transfers 1.2 times 10 to the 6 joules of energy to the turbine. The total mass of the turbine blades is 16,000 kilograms. The wind causes the turbine blades to accelerate from rest to an average speed of 7.6 meters per second. Calculate the efficiency of the turbine. So the efficiency is equal to the useful energy output. In this case, it's the kinetic energy of the turbine, so 1/2 times m times v squared over the wind energy. So energy from the wind, okay, times 100. Okay, so let's plug in the numbers. So 1/2 times 16,000 times 7.6 squared over 1.2 times 10 to the 6 times 100, okay, which is 38.5%. Okay, let's move on. Question 8. A student investigates the speed of sound by making a loud sound in front of a large wall a long distance away. The diagram shows the position of the student and the wall. The sound reflects off the wall and back to the student. Give an appropriate method for measuring the distance between the student and the wall. So use a tape measure. Use a tape measure or laser range to measure the distance, to measure D. Okay, so this is D, I guess. Okay, take the measurement more than once. Okay, and average to reduce random error. Okay, part B. The student uses a stopwatch to determine the time taken for the sound to travel from them to the wall and back again. The distance from the student to the wall is 65 meters. The student measures a time of 0.35 seconds when the sound has traveled to the wall and back again. Calculate the speed of sound from the student's data. Okay, so the distance traveled is equal to the velocity, the speed of sound times time. But because we measure for back and forth, we have to divide by 2. Okay, so I mean the time measured is for the sound to go back and forth. So it's like we are having 2 times that distance. Okay, so maybe if I write it like this, it will make more sense. So 2 times s is v times t, but we are interested in v, so v is 2s over t. So 2 times 65 over 0.35 yields 371.4 meters per second. Not bad at all. The actual number is 340 meters per second, but it's not bad for such a primitive method. Okay, so it sounds good to me. Let's move on. Part C. Evaluate this method for determining an accurate value for the speed of sound. So first of all, the student did the measurement once. The measurement only once. Okay, so any random errors, okay, are not reduced. Okay, human reaction time, okay, introduces error into the timing, both when starting and when stopping the stopwatch. Okay, I'm gonna move to the back because I will need some extra space. Okay, the distance measurement. So the distance measurement with a basic instrument may not be accurate. Okay, over such a large distance. By the way, you don't have to write all these. 4 points are enough, 4 sentences, but I'm writing everything for completeness. Okay, at very large sentences, oops, what am I saying? So, at very large distances, okay, the echo may become too quiet to hear. Oops, too quiet to hear. Okay, making timing challenging. Okay, using a large distance, okay, is actually an advantage. Okay, because the time interval, okay, becomes larger, which reduces the relative effect or just the effect of reaction time. And finally, uncontrolled variables such as wind, air temperature, and noise could affect the result. Okay, as I said, 4 out of these 6 points I wrote are enough to get you full points, I believe. But I wrote everything I could think of for completeness. Okay. D, explain an improvement to the student's method. So you can use a microphone. So use a microphone connected to a data logger. Okay, to detect both the original sound, okay, and the returning echo. Okay, this will remove human reaction time entirely. Okay, so this was paper 2 from November 2024. I hope this is useful to you guys. Let me know in the comments if you have questions. Let me know where you are watching from. It's interesting. And see you in the next video. Okay, I have nothing more to say. Like and subscribe as usual, and so on.